Very happy today to have Dr. Ingrid Cnossen here to give our colloquium. And Ingrid received her PhD in atmosphere physics from the University of Leicester in 2009. And she worked for about 2 years in British Antarctic Survey as an atmosphere modeler for, I think there's overlap between your PhD and British Antarctic Survey a year. Maybe your part of your research was done there. And then he came to HAO as a postdoc visitor. And then she received the Natural Environment Research Council Fellowship. And on that fellowship, she returned to Bath. She's currently a research fellow there. And she's visiting HAO for a few months. And her main research focus has been the long-term change in the middle and upper atmosphere, especially the effects of decadal to centennial changes of Earth's magnetic field on the whole atmosphere system, which she will discuss more today.
Okay, thank you very much for the introduction, and thank you all for coming. I'd also like to acknowledge a couple of people who have contributed to the work I will present today. So Art Richmond and Mike Wildberger helped me while I was a postdoc here at HAO. Christian Franske is a colleague from British Antarctic Survey who helped me with some time series analysis, and I've just started working with Hanli as well on the downward connection bit of my talk today. So I've been interested in long-term changes in the upper atmosphere. So those are multi-decadal changes happening over the past 50 years or so. We've seen cooling in the upper atmosphere. And also the middle atmosphere, and that global cooling is at least qualitatively consistent with the expected effect of increased greenhouse gases. You see cooling happening throughout the middle atmosphere and most of the thermosphere. Only here in the lower part of the thermosphere you might see a little bit of apparent warming and that's really because when the whole atmosphere is cooling, it's contracting, and that means that all the atmospheric layers are moving downward, and that's causing this whole temperature profile to move down. So if you're in a fixed height reference frame, you'll see a little bit of warming in the lower thermosphere. And then as a consequence of contraction of the atmosphere, you also expect ionospheric layers to move downward, and that's kind of seen in the lower part of the ionosphere. If you look at the F2 layer ionosphere, the picture gets a bit more complicated. So people have looked at the height of the peak in the F2 layer, called HMF2, and also at the critical frequency of the F2 layer, which is FOF2, and related to the peak electron density, which we refer to as NMF2. And the thing is that the trends really vary a lot from location to location. So in some places you might see a decrease, as you would expect, but there is a lot of variation in the amount of decrease in HMF2 as well. And it also varies with seasons, it varies with the local time that you're looking at. So it's quite complicated. And then in some locations you'll even see an increase in HMF2, which is completely inconsistent with what you would expect from increased greenhouse gases. So something else must be going on there. Also, significant trends are reported in FOF2, so related to that maximum electron density in the F2 layer, and for a decrease in an increase in greenhouse gases, you would actually not expect much of a change in FOF2 to happen. So there's probably other factors playing a role in that long-term change in the upper atmosphere as well. And as Hanli said, I've mostly worked on the effects of magnetic field changes, and it is contributing. And I'm going to start my talk explaining how that happens. So we'll look at some idealized modeling studies where I've played around with the Earth's magnetic field strength, as well as the orientation of the magnetic field, just assuming a simple dipolar magnetic field. And that's really good to kind of understand what the main mechanisms are of how the Earth's magnetic field can contribute to these long-term changes. But it might not be the only other important factor. Another factor is any long-term change in the sun, because the sun has a very strong influence on the upper atmosphere. So if there's anything changing in the solar output, that could also have a possible effect. And I've recently started looking at this more from a data analysis perspective, observational records. So I'll show you an example of that as well. And then at the very end of my talk, I'll come to the possible downward influence of magnetic field changes. So most of the simulation studies that I'm going to show are based on the coupled magnetosphere, ionosphere, thermosphere model. So a model of this entire domain here. We specify the solar wind conditions on the outer boundary of the model. So solar wind speed, solar wind density, and the direction of the and strength of the interplanetary magnetic field. And we let that interact with the Earth's magnetosphere, and then at high latitudes that is coupled to an ionosphere thermosphere model. So the model is built up of this magnetospheric part called the LFM, the Lyon-Feather-Mowbray MHD code, and that is coupled via the high latitude electric potential and particle precipitation information that is going into the TIE GCM, the thermosphere, ionosphere, electrodynamics general circulation model. So this takes care of the ionosphere, thermosphere part of the domain. It takes that input from the LFM part of the code, calculates a lot of thermospheric and ionospheric parameters, and one of the things that it's calculating is the ionospheric conductivity, or the vertically integrated conductivity called the conductance. And that is important as a boundary condition for the magnetosphere, because currents that flow into the Earth's upper atmosphere along the magnetic field, they can close through the Earth's ionosphere, and then you need to know about the ionospheric conductance to see how much current you can support. And that feeds back into the LFM. That's how the whole system is coupled. So both the magnetosphere can influence the ionosphere and the thermosphere, but also the other way around. So I use this model to look at changes in dipole moment to start with. In kind of the last few centuries, we've seen mostly a decrease in the Earth's magnetic field. Since about 1840 or so, the Earth's magnetic field has been decreasing at a rate of about 5 to 7% per century. Before that, it's a little bit more difficult to figure out what was exactly going on. There are also indications of the Earth's magnetic field strength on geological timescales, and that's shown here. So we have the present day here, and this is going back 800,000 years into the past. At the moment, the magnetic field is relatively strong, even though it's been decreasing over the past 170 years or so. So we're at a level of about 8 times 10 to the 22 ampere meters squared. But it's been varying over a large range of values. And it's kind of that range that I was exploring in my idealized simulation, so going from about 2 to 10 times 10 to the 22 ampere meters squared. And I just did some relatively short simulations for March equinox conditions. They're all 36 hours long, and we use only the last 24 hours for analysis to allow the model to reach more or less a steady state. The solar wind conditions are constant. We have constant density, a constant speed of the solar wind coming directly to the Earth from the sun, and the IMF is southward continuously. So this is not realistic, but it's just to explore what's going on if you change the dipole moment. And I also selected 3 different solar activity levels to work with, because the solar activity level controls the ionospheric conductivity, and that's one of the important parameters in this. So the Earth's magnetic field also directly... yes?
This includes variation in the strength of the magnetic field going back a long time. How certain is that? In terms of systematic errors, not just the statistical error that is represented.
I think it's not incredibly precise, but given the huge range, I certainly think that it can vary a lot. Up to 50% of present day to more than 10% or so, quite easily. But it is difficult to figure out Earth's magnetic field strength. But it's not really my personal expertise, so I don't know too much about this either.
The idea that how that is induced, that one tracks how magnetic orientation is frozen in when volcanic or basal material is cooling. Is that the source?
Yes. It comes from rock samples, and you can. I think they demagnetize the rocks in the lab, and depending on how high a temperature you need to get rid of the remnant magnetization in the rock, you can figure out how strong the magnetic field must have been at the time that it was frozen in. I think that's what it's based on. Okay. So the Earth's magnetic field strength directly influences the Earth's ionospheric conductivity, because the stronger the magnetic field is, the more ions and electrons are bound by that magnetic field, so they have less freedom to move. So the stronger the magnetic field, the lower the ionospheric conductivity is. You can derive these scaling relations. So each point here on the plot is one of my simulations. This is a global mean and also integrated in the vertical. So this is the Peterson conductance as a function of dipole moment, and this is the Hall conductance as a function of the dipole moment. And I fitted these lines through it because they more or less follow these kind of relationships, so you can derive scaling relations that describe how the conductance depends on the dipole moment. And there is a little bit of dependence here in the Peterson conductance on the solar activity level that you choose as a background condition, but not so much for the Hall conductance. Then another direct effect of change in the Earth's magnetic field strength is that you're going to change the size of the magnetosphere, because the size of the magnetosphere depends on how much magnetic pressure you've got inside the magnetosphere to balance against the solar wind dynamic pressure. So here we look down on the magnetosphere with the sun on this side. These magenta crosses are for the strongest simulation, and we get the strongest magnetic field, and then we go inwards towards the weaker magnetic field, so a smaller magnetosphere. And if you look carefully, you can also see that the shape of the magnetosphere changes slightly. So for this case, it's a more blunt magnetosphere, and if you go to the really low magnetic field strength, you get a little bit more of a pointy magnetosphere, if you like, which is in part related, we think, to the ionospheric conductivity, which influences currents that flow in the magnetosphere, and these currents form loops that in themselves create small magnetic fields, and that can just add a little bit of magnetic pressure in some locations and take it away in others. As you change the size of the magnetosphere, you also change where the boundary occurs on the Earth's surface between field lines that are closed on the Earth's surface and field lines that extend out into the solar wind. And that boundary I call the polar cap boundary, so I consider the area inside of that boundary to be the polar cap. And you can plot the latitude of that polar cap boundary, again as a function of dipole moment. Here are all my simulations again in the colors. And you can see that when you decrease the dipole moment, you move that boundary to lower latitudes, so you increase the size of the polar cap. It's also possible to derive a theoretical relationship just based on what you would expect the size of the magnetosphere to do as you change the dipole moment, and that's this black line here. So you see that if you don't move too far away from the present day situation, then that theoretical relationship does reasonably well. But when you move to the really low dipole moments, it starts to deviate from that because of the influence of the ionospheric conductivity again. Another variable that changes is the cross-polar cap potential. This is a really useful measure of how strong the driving is of the magnetosphere from the magnetosphere on the upper atmosphere. Also this, when you decrease the dipole moment, you decrease that cross-polar cap potential. You can derive a theoretical relationship also for cross-polar cap potential. And again, the same thing, it works reasonably well if you don't go too far from the present day value, but for the really low dipole moments, it doesn't work so well anymore. Okay, so when we increase the size of the polar cap and at the same time decrease the cross-polar cap potential, it means that the electric field is going to be decreasing as well. Now, a decreasing electric field is important for E cross B drifts. E cross B drifts scale as E over B, the strength of the electric field divided by the strength of the magnetic field. But of course, we're changing B as well. So it just depends on the balance of how quickly both of these are decreasing compared to each other, what's happening with the E cross B drifts. And that scaling for the strength, for the magnitude of the E cross B drift is plotted here as a function of dipole moment. And you see that if you go from the present day to a weaker dipole moment, then initially you will get stronger E cross B drifts, but eventually they'll grow weaker again. And that has consequences for Joule heating of the upper atmosphere as well, because that's in part related to how strong those E cross B drifts are, and you see that the Joule heating follows a very similar sort of pattern. And of course, once you change the Joule heating, you change the energy input into the upper atmosphere, and you can change the temperature in the upper atmosphere as well, and we'll see that later on with more realistic simulations. So for now, I want to move on to effects of changes in the orientation of the dipole. So I played around with the dipole tilt, which is the angle between the geographic axis and the magnetic axis. This figure here shows how the tilt angle of the best fitting dipole to the Earth's magnetic field has changed over time. So the last bit is based on the International Geomagnetic Reference Field, the IGRF, and this is based on another model. So at the moment we're at a tilt angle of about 10 degrees. It was a little bit larger back in before 1950 or so, and if we go further back in time it was maybe as low as 5 degrees. Again, there are also larger variations that occur on geological timescales. And another interesting thing is that actually it's not, the Earth's magnetic field is not exactly a dipole, and the north magnetic pole especially has been moving really rapidly. So there are also kind of different situations in the northern and the southern hemisphere. So you could kind of look at it as the northern hemisphere having a different tilt angle than the southern hemisphere has as well. So some of these results can help to explain differences between the two hemispheres as well. So what's the effect then of a change in tilt angle? So we're first looking at diurnal variation of a couple of different parameters. So this is here at the top the northern hemisphere cross-polar cap potential, the same for the southern hemisphere. Then the Peterson conductance in the northern hemisphere and southern hemisphere, and the Joule heating in the northern hemisphere and the southern hemisphere. And this is all, these are hemispheric averages centered over where the magnetic poles are. So basically when you have high conductance in the northern hemisphere over here, that's because the northern hemisphere at that point is tilted towards the sun, so you get more conductivity over the polar cap regions in the northern hemisphere. What you see in the cross-polar cap potential is that for a zero dipole tilt, the black line, there's very little diurnal variation. That's because over the course of a day at equinox, this is an equinox simulation, you get no variation in the angle between the Earth's magnetic axis or rotation axis with respect to the sun, no motion away or towards the sun over the course of a day. But as soon as you start introducing a tilt angle, you will get a motion of the magnetic axis towards and away from the sun over the course of a day. And the stronger that tilt angle is, the stronger that is the case, and you get a dip in the cross-polar cap potential when you introduce such a tilt angle. And that's basically because at that point the angles between the Earth's magnetic field and the solar wind are not optimal anymore for coupling. So you get a less efficient coupling if you have a larger angle between the solar wind and or the interplanetary magnetic field and the Earth's magnetic field that's not exactly anti-parallel. So you get those dips in cross-polar cap potential. They're not exactly the same for different times. I think my pointer is stopping to work. Yeah, I think it's dead. Do you have another one? Okay. So if you look at the dip around 16 UT, it's not exactly the same as the dip around about 4 UT, and that's because of the influence of the ionospheric conductivity. So that kind of modifies that pattern a little bit, but it's quite difficult to see in the cross-polar cap potential. In the Joule heating, the same happens. Oh, I've got a little bit left. The same happens, so you have a more prolonged dip in here in the northern hemisphere when the ionospheric conductivity is low, and it's less of a pronounced dip in the Joule heating when you have a high conductivity. Now for solstice, the whole pattern becomes a little bit more complicated because you already are with an angle towards the sun or away from the sun, depending on what hemisphere you're in. So also when you modify that over the course of a day as the Earth's magnetic axis kind of rotates around, you get a more complicated pattern that's not just a dip here and a simple increase here. It depends on how much of a tilt angle you have compared to the 23.5 angle that the Earth's rotation axis already makes with respect to the sun. So the pattern is a bit more complicated, but the same kind of ideas still hold. So now we're looking more at geographical patterns. So these are 24-hour averages now. So we average out. This is just equinox results, just to show you an example of what a change in tilt angle does. The tilt angle is 0 in these top plots over here, and then 30-degree tilt angle here, and this is the difference between the two. This is the Joule heating. You see at high latitudes, there's most of the Joule heating. It's a very symmetrical sort of pattern, which you would expect because the poles are exactly at 90 degrees. If you move the pole is in this longitude sector and over here. So the northern pole is at 70 degrees west, and you see that the Joule heating follows the magnetic pole around, as you would expect. And also, if you look at the magnitudes, the magnitude of the Joule heating on average over the 24 hours is lower, and that's because of those dips in Joule heating that you get over the course of the day. Temperature kind of follows the Joule heating more or less. So you see increases here in the vicinity of the magnetic poles in temperature, or relative increases with respect to those areas. And this is then the difference pattern that you get out.
Question?
Yeah?
Is that a certain height or exosphere?
Sorry, yeah. This is at about F2 region height, so this is in the thermosphere. Yeah, I got a little bit back, but okay, thanks. So this is the same again for HMF2 and NMF2 now. So very symmetric pattern when you have no tilt angle. If you introduce a tilt angle of 30 degrees, then these structures follow the magnetic equator around. And this is the difference pattern that you get in this case. So and when I looked at this to try and explain what is really the driving force behind these changes, then in case of NMF2, it's partly related to ultimately changes in Joule heating, which affect upwelling and downwelling near the polar regions. So in the region of the new magnetic pole, you get more upwelling, and that means more molecular rich air comes up, so the O to N2 ratio is going down, and that means that you get less ions in that region, so NMF2 goes down as well. So that's part of the story for NMF2. But also changes in the vertical diffusion along the magnetic field make a difference. And that's for both NMF2 and for HMF2. But for HMF2, that's really the main mechanism that is causing those changes. So far we've just looked at southward IMF conditions. So now, if we look at northward IMF conditions, of course, Joule heating is much less important. So also changes in Joule heating are much smaller, and the changes in the temperature are much smaller. And as a result, those changes in upwelling and downwelling are also much smaller, and that means that some of the response that we saw before in NMF2 disappears, but we're still left with the effect caused by changes in vertical diffusion along the magnetic field lines, which have a vertical component. So in HMF2 doesn't change much because that was mostly a process that was internal to the ionosphere, that vertical diffusion along the magnetic field. So responses in HMF2 remain the same. NMF2 does depend a little bit on the solar wind conditions that you've got. Yes?
When you calculated the changes of temperature, is that the same 36-hour run?
Yeah, what I showed before, yeah, it's 36 hours simulation and using the last 24 hours only. Yeah. Okay, I'm going to move on to more realistic magnetic field changes now. So this is based on the International Geomagnetic Reference Field, which describes the structure of the Earth's magnetic field. This was the field in 2008 in terms of field strength, so this is the intensity. And this is the difference between 2008 and 1908. So we have this weak area here, which we know is the South Atlantic anomaly region, and that region has been intensifying and broadening over time. It seems to also move westward a little bit. And this figure shows contours of constant inclination. So zero inclination means that you're at the magnetic equator. 90-degree inclination is at the poles, and then there are some intermediate ones in there. The black lines are for 1908 and the red for 2008. So you see a westward and a northward movement of the magnetic equator over time. And also you see that in other structures as well. And this is just a difference pattern between the two inclination angles for the 2 years, I mean. So the strongest changes are happening in this region here, which I will refer to as the Atlantic region because it's mostly over the Atlantic Ocean. These simulations that I did with more realistic magnetic field changes also have a more realistic setup. So I use real solar wind data in this case, and a longer simulation of 15 days long, going from 20th of March, 0 UT, to the 4th of April, 0 UT, in, well, we use the solar wind conditions of 2008, and also the solar minimum conditions that were happening in 2008. Mostly geomagnetic activity is low, and because we now have 15 days worth of simulation, I can give some information about the significance of the differences between two simulations against the day-to-day variability that occurs within a simulation. So these are some results for HMF2 and FOF2. So HMF2 on this side, and here FOF2. This is for 14 UT. Which means that it's daytime in the area where we expect the strongest changes to occur. This is the control case for a magnetic field of 2008. This is the difference between 2008 and 1958. So only the magnetic field has changed, nothing else. And this is the difference between 2008 and 1908, again for only a change in the Earth's magnetic field. So in HMF2, you see this response is strengthening basically if you look at the longer interval, and the same is happening here. You get a stronger response. And these differences are really quite large. They can be up to minus 50 kilometers or plus 30 kilometers, which is quite a lot. And here as well, down to minus 1.5 megahertz. And if you look at the magnitudes of FOF2 here, then that's a significant fraction. Most of these effects are due to changes in plasma transport terms. So again, the vertical component of diffusion along the magnetic field, but also we found that vertical E cross B drifts change and contribute to this as well, and vertical plasma transport that is induced by horizontal neutral winds that can either push ions and electrons up or down magnetic field lines that also changes. So most of these responses are due to processes that are internal to the ionosphere, not so much the ones that were related to the solar wind conditions and what's happening in the magnetosphere. So for the rest of my presentation, I will now look at just the TIE-GCM simulations, which I use to compare the effects of magnetic field changes to the effects of CO2 changes. So that's over here. So this is just based on TIE-GCM simulations. They are a bit longer as well. I ran from 1st of March until the end of April. So this is 2 months worth of data, and this is the average over the 2 months for 12 local time. So I moved to a local time reference frame in this case because a lot of the observations of long-term change in the upper atmosphere are done in a local time reference frame. Usually a station will do a sounding of the ionosphere at local noontime, so a lot of the trends are for noontime as well. So I wanted something that was as comparable as possible to a map that you might make of observations of long-term change in HMF2 and FOF2. So this is the control for 2008. And then I did a simulation where I changed only the CO2 concentration back to the level of 1908. So this has both the magnetic field of 2008 and the CO2 concentration of 2008. If I reduce, or actually the difference is taken in the opposite sense. So this is the effect of the increase in CO2 concentration since 1908, and that's about a 5 kilometer decrease almost everywhere. The shaded areas indicate where it's statistically significant. So it's not significant everywhere, but it's a fairly uniform response of minus 5 kilometers. Then in FOF2 we get nothing because I would have had to make the contour levels very, very small to be able to see anything here, and there's no significant response in FOF2. And that's basically what you would expect based on previous simulations and based on theoretical results as well. Then for the magnetic field effect, so this is the difference between that control simulation here and a simulation where I changed only the magnetic fields to the level of 1908. Then you get again strong changes over here. You also see some significant areas of change now in other regions. That's probably because this is a longer simulation than what I showed before, so you have more chance for a signal really to stand out against the background noise. And also in FOF2 you get again the strongest changes over here. But the main thing is, I would say that when you compare these two effects, the magnetic field effect is certainly more important for FOF2, and even for HMF2. It depends a little bit on where you are, but it can be of a similar order of magnitude, about 5 kilometers, or it can be much stronger than that. And then I also wanted to look at the neutral temperature again. This is again at about it's about 300 kilometers. This is the same setup as before. So this is the control. This is the effect of the increase in CO2 concentration, and this is the effect of the change in the magnetic field since 1908. The CO2 effect is about an 8 Kelvin decrease in temperature, very uniform again. The effect of a magnetic field change is less uniform. You get a 4K increase in a lot of places, but near the magnetic poles you can get either a decrease or an increase, but hardly anything here is significant. There's a tiny patch there that comes up as significant, but that's it. So really on its own, this is not a significant response. But if I look at the magnitudes here, I thought, well, the magnitudes aren't that different from what I see for the CO2 effect. So I did one additional simulation in which I changed both the magnetic field and the CO2 concentration back to the 1908 level. So this is kind of the added effect of CO2 increases and changes in the Earth's magnetic field. And then I would say that this does look quite different from this figure. So even though the effect of a change in the magnetic field is not significant on its own, it does seem to change the response quite substantially if you compare it to the CO2 effect alone. So you can't really ignore it either. So now I'm going to change to a bit of a different topic. This is more focused on trend analysis from Ionosphere records. I just want to say briefly about the most common technique that is used to find long-term trends in Ionosphere data, so in HMF2 or in FOF2. This is an example for FOF2. The most common technique is to first try and correct for the influence of the solar cycle. The black line here is the FOF2 record. This is a yearly mean record, and I think it's also averaged over all local times in this case. And so the first thing you do is to do a linear regression with F10.7, or you could use a different solar activity indicator if you want, but F10.7 is commonly used. And you can calculate the fit, and the fitted line is that red line here in this case. And you calculate the difference between the two, that's the residual. That should be the signal in FOF2 that has no solar activity influence anymore in it. And then you do another linear regression with time to find the linear trend. And in this case, that comes up with minus 14 kilohertz per year. You can do an F-test or a T-test, which is the same thing in this case, to try and figure out whether this is significant. There are a few problems with this method. First of all, you have to assume that the trend is linear, and you don't know if that's going to be the case, but it might be fine. The other thing is, I don't think that the correction for the solar activity is ideal in here, because basically you make one correction for solar activity levels, solar activity on all timescales. So you remove the solar cycle, but you also kind of remove any long-term variation in the sun, or longer timescale variation, or shorter timescale variation. But there's only one regression coefficient. So I don't know if that really works so well. And if it doesn't, that means that you can't really trust that residual very well. So I was introduced to a new technique by a former colleague, Christian Franzke. He's been using this technique called Ensemble empirical mode decomposition, and he's applying it to tropospheric data, to temperature records stations around the world. And I decided that I wanted to try and apply this to ionospheric data, and it can equally be applied to F10.7, so here I've applied it to F10.7 itself. This is a method that decomposes a time series into cyclical components, and then when it can no longer find any more cyclical components, you're left with a residual, and you can interpret that residual as a long-term trend. And it's a mathematical decomposition, so it makes no assumptions on what this trend should look like. So that's an advantage. Another advantage, I think, is that because it takes care of those cyclical components, you get rid of the influence of the solar cycle as part of the trend detection method as well. It does everything in one algorithm. So in this case, it's applied to f10.7. You get the first IMF, that's the high frequency noise comes out. Then this second IMF looks a lot like the solar cycle signal. This is a bit longer term variation, another longer term variation, and this is then the residual in this case that you end up with. And equally, I should actually say, yeah, it looks like there's an overall decreasing trend in f10.7 in this case, but we don't know if it's significant. So the next step is to try and do some significance testing. So I'm following again Christian Franzke here, and you can generate an ensemble of synthetic time series that share some characteristics with the original data. I do that with two different techniques. One is a phase scrambling technique, where you have the same power spectrum as the original time series, but you randomize the phases, so you get a whole number of new time series that kind of look like the original time series, but don't contain a long-term trend. That's the main thing. And another way of doing this is to define a cyclical AR process. So I do those two methods. Then the synthetic time series contain no long-term trends, but I can still apply that EEMD analysis on it, and then find the distribution of trends that you can expect when there's not really a trend present, because we know that. So if the trend that you find in the original data is really in the tails of that distribution, then you can say with some confidence that it's probably significant. Now, in the case of f10.7, I find that it's not significant, so there's no significant long-term trend according to this technique. And I can also apply this to Ionosphere data. So I did, again, an example for FOF2 from Sodankila here. So we have the original time series, and then it's broken up in these different IMFs, and a residual, which is, again, decreasing. And if I look at whether that's significant, then it seems that it's significant against the ensemble of time series that was created with phase scrambling, but not against the AR process, if we assume that as our null model. We get a slightly stronger trend in this case. This is minus 22 kilohertz per year. So it's about 1.5 times stronger than the linear regression trend. And I kind of wonder why it's different and if it says something about the sun, because of course in this method we don't correct for any long-term solar variation, so any residual in solar activity still can have its influence on the ionosphere in here, whereas for the linear regression method you correct for that as well. And I'm not completely sure yet if that's the case. I did some additional work. Of course, this was only one example, but I did the analysis on about 20 stations that had sufficient data. This is, again, the Sodankila example, but now plotted together with the residual in f10.7. Some of those stations give significant trends. It's about half, I think, of the 20 stations or so. And there's a really high correlation between the significant trends in FOF2 and f10.7, and also in HMF2 and f10.7. So I do wonder if there's maybe more of an influence of the sun on those trends than what people have previously thought as well. Okay, and then finally, I want to say a few things about this possible downward connection of long-term change in the upper atmosphere. So the question is whether a persistent change in the thermosphere and ionosphere can affect the atmosphere below. And I'm coming back to magnetic field changes now. I did 2 38-year-long simulations with the extended version of the whole atmosphere community climate model, WACM-X. So one simulation has the magnetic field of 1900, the other has the magnetic field of 2000, and for the rest, both simulations think that it's the year 2000. So it has relatively high solar activity level, but geomagnetic activity is fairly moderate. Of course, Wacom doesn't have the electrodynamics that the TIE-TCM has. So I'm missing some of the responses that I can capture with the TIE-TCM. However, I do get the effects of any movements in the auroral oval with Wacom because it still receives a high latitude forcing of the high latitude electric potential is imposed, and depending on where the magnetic poles are, that will move around. Also in Wacom, and so you get any processes associated with the auroral oval also move around accordingly. And this is an example of a map of neutral temperature. This is for January. This is an average over the 38 years. This is the control for the year 2000. And this is the difference between the 2000 and the 1900 simulation. I don't completely understand this yet. This is a very, very new result still. We see a strong increase here in temperature. I was expecting it near the poles as we find it, and I was expecting it to be largest at these high latitudes. But I wasn't really expecting it to be this large in the southern hemisphere. If anything, I thought it would be larger in the northern hemisphere. So I'm still trying to figure out exactly why it appears like this. It seems to be a seasonal effect because the response in the northern hemisphere becomes larger in June and July, and this one in the southern hemisphere is larger during December and January. But at least there's a decent difference in the upper atmosphere here, and then we can still see how does that propagate further down, or how does it influence the atmosphere further down. So I did a few cross-sections. These are zonal means, vertical cross-sections. So this is neutral temperature. Here the control again, and this is the difference. The same for zonal wind and the meridional wind. And you do see a couple of things going on in the temperature. There seems to be a weak decrease in temperature here, and also here very low down actually, which I wasn't expecting. You also see some things happening there, but they're not significant, even though they're bigger than in the southern hemisphere. And in the zonal wind is actually maybe the most interesting, because this is such a deep response here of change in the zonal wind. Also a little bit here in that same sort of location is where we saw the decrease in temperature. And this seems to extend all the way down to the troposphere, which I'm really kind of puzzled by, and I'm not really sure why it's happening, and especially why it's happening in the southern hemisphere where it's summer. If anything, I thought winter would be more likely. But in any case, this is what's coming out at the moment. Not that much going on in the meridional winds. I have to do a lot more work on this to try and explain the results. I really don't understand it very well at the moment, but if anyone has ideas, I'll keep my ears open for that. So I'll come to my conclusions now. I've shown you that changes in the magnetic field strength can affect the ionosphere through changes in the conductivity, the size of the polar cap, and the high latitude electric field, which then affects the E cross B drifts and the Joule heating. Also changes in the tilt angle affect the upper atmosphere through changes in Joule heating, and also through changes in plasma transport processes. Then realistic magnetic field changes produce the strongest effects in the Atlantic region, and especially for HMF2 and FOF2. That's quite important. Magnetic field changes also affect the neutral temperature at 300 kilometers, but it seems that like it's not significant on its own, and yet you can't really neglect it because it does seem to modify the response of the effect of CO2 on its own quite significantly. I think more work is still needed to try and clarify the role of long-term solar variability in long-term change of the ionosphere better. And I have some really interesting initial results that seem to indicate that the magnetic field might, or the influence of the magnetic field might extend much further downward than I was expecting. But I really need to understand still how this would take place. And then finally, a quick announcement. I'm involved in organizing a workshop this summer at the British Antarctic Survey, or it will be held in one of the old colleges in Cambridge. It's on long-term change and trends in the atmosphere. Most of it is focused on the middle and upper atmosphere, but we also welcome some contributions from the lower atmosphere as well, especially when they are relevant to the changes that we see higher up. The website is up and registration should be opening very soon, I think. So some of you, I hope to see there. Thank you very much.
Questions for Ingrid?
Yeah, the direct effects of Joule healing probably are extend down to what, maybe 100 kilometers at most?
The direct effects of Joule heating, you said?
Yes.
Yeah. And also, the strange thing is, when I'm looking in the upper atmosphere at the same vertical level as this, then the strongest Joule heating change isn't actually happening in the southern hemisphere. It seems, if anything, the Joule heating change is larger in the northern hemisphere, which doesn't explain this result. So even the upper atmosphere response that is produced here, I don't really understand.
Okay. I was going to speculate that you're seeing some sort of teleconnection effect, butterfly effect, but that's
Yeah, I don't know yet.
Can you give an idea, this new decomposition method of sort of beyond the fancy name that starts with Ensemble something, how that is different from harmonic analysis in terms of Fourier decomposition or Hilbert decomposition?
I think with the Fourier decomposition, you have to have the same amplitude throughout for a particular component, so it's a wave that has the same amplitude throughout, whereas this method doesn't assume that the amplitude of a signal with a given frequency has to be constant throughout the time series. So it's a different way of doing things. Well, in that it decomposes the time series into cyclical components. I don't know if you should call that harmonic or not. I don't know.
I think it's a bit like a wavelet, but it doesn't have a fixed base. The base is an empirical base. And what they claim is it's a better alternative to wavelet analysis because it can capture the time variation of things.
It must be similar to what we call empirical orthogonal functions.
I'm not sure that it is. I don't think it is. I think it's a different sort of mathematical description than that. And empirical orthogonal functions, they are spatial patterns, right? Can you apply that to a time series?
You can do an EOF analysis on a single time series.
Okay.
I don't. Going back to Wacom X, how realistic is the ionosphere in it? The ionosphere in Wacom X.
Sorry?
How realistic is it?
How realistic the
have
ionosphere is?
Transport, it's mostly photochemistry, as I understand.
Yeah, you're probably better at answering that. I mean, it doesn't have the electrodynamics in there, so that's an important thing that's missing, and they're working on that to get that in there at the moment. So yeah, the ionosphere is not as good as in the TIE GCM. I don't know how realistic you can call it, but.
How is it? Is Joule heating cup?
Well, there's a high latitude electric field that's imposed in the upper atmosphere. I'm not sure actually how the Joule heating is calculated, if it's calculated from...
It's equivalent to the TIE GCM, time GCM methodology. You have an auroral oval, you have an opposed electric field, and you calculate for high latitude.
For Joule heating, because you have even motions, the neutrals, the ions. But the ions don't move like an X, so are they
You do have an auroral ionosphere with a convection, implied convection, and you calculate Joule heating the same way you would in IGCM or time GCM through an assumption of an electric field potential path. So that part, I mean, basically that part is what you're seeing in the wacom simulation at this time is the effect of moving or changing the auroral force and heating that comes from that. So this, if anything is here, it's a heating effect. Although I would suspect, Dan, if I want to comment, I would suspect that with one ensemble that we can't say too much about the middle atmosphere. But this is just one run.
It is one run, but it's 38 years long.
So this is an average over the 38
It's an average over 38 years.
38 years, okay.
Yeah.
Excellent.
Does this work? There's obviously going to be year-to-year variations in that 38-year run. Have you looked at the variance over that 38 years and compared the difference between these two simulations with the magnitude of the variance over each of those 38-year simulations?
Oh, you mean variance within the year or variance between years?
Over the 38 years of each run, there's going to be a year-to-year variation. So there's going to be a standard deviation.
Yeah.
There's going to be a mean year, which is what you're showing.
Yeah. That's basically what's going into the significance calculations, because that's just a t-test between the two simulations. So that's taking into account the standard deviations that you get over the 38 years compared to the means.
Magnitude of the standard deviation.
I haven't looked at the magnitudes themselves, but the shading, which is a statistical significance, should indicate where the differences are basically large compared to the standard deviations.
Have you looked at the difference in the NO cooling? I know that you've shifted the auroral oval, so you've put NOx in a completely different location. And I would have thought that may be what's driving, say, these temperature changes in the lower thermosphere.
Yeah, I've started looking at it, but the results are still really fresh. I don't think it obviously explained it, because then I would have thought, okay. So I quickly looked at it, but I can't tell you exactly what was going on. But it's not obvious that the change in NO cooling is explaining what's going on there. So, yeah.
Maybe just one comment. Your message seems to be that CO2 isn't really a big driver of variability.
It's part of it, but it's not the whole story. Yeah.
In the TIE-GCM, you're not really handling any variation in the lower atmosphere, right? So you have a fixed boundary condition. I don't know if you vary the boundary condition, but you don't have any wave differences coming out from the lower atmosphere.
Mm-hmm.
So I think you haven't closed the book on whether there's influences in climate change, influences in the lower atmosphere that could affect the upper atmosphere.
Oh yeah, I think climate change variations that go further than just the CO2 effect. So this is just the in situ effect of changes in CO2 concentration. And I did vary the lower boundary a little bit to account for the fact that the lower boundary is slightly different temperature depending on how much CO2 you have. But yeah, wave effects are another possible source of long-term change in the ionosphere. If you have a long-term change in either how much wave energy is being generated in the troposphere and propagates all the way up, or you have a change in the filtering conditions in the middle atmosphere, then that's another possibility, yeah.
So just so Dan doesn't get the wrong impression, was the global mean change in temperature in the atmosphere caused by these magnetic field changes?
Well, that will be smaller again, yeah, global mean, because it's different in different locations, so you can get, so yeah, if you look at that figure there, you can get...
So when we're talking about the measurable effect on thermospheric climate, which is mostly quantified by satellite drag measurements, measuring the global mean change in temperature directly.
Yeah, if you look at the global mean, then it will be smaller.
CO2 effect is large, not nearly as large as the solar effect, of course. But then you have the magnetic field effect, and then you have maybe other things, changes and all of that conditions. I'd be curious, you showed the time series analysis of the F-10-7, largely as a test of the method.
Mm-hmm.
But you only did it for 2005.
Yeah.
And it was, you said it wasn't significant in terms of the long-term trend, but it was close.
Right.
So I'd be curious to know if you added the next 9 years.
Oh yeah, I could easily do that. I didn't.
The boundary and the significance.
Yeah, especially with the low solar minimum of 2008 and 2009, you might get something significant. I deliberately avoided that here because I didn't want to get into kind of those unusual conditions of the solar activity. But yeah, I can easily do it for up to 2012 or whatever. Yeah.
Maybe you mentioned this, I missed that. So the part you were looking at the trend at Finland, is that try to compare with your earlier observation, see if they get the same trend?
Well, yeah, that's ultimately the plan. Actually, in the location of Sodankylä, which is in Finland, if you look at this figure here, then you can see that Finland is pretty much on the zero line when it comes to, or northern Finland anyway, is pretty much on the zero line when it comes to magnetic field effects. And the effect of the change in CO2 concentration is not actually significant at that location, although you might still see some effect there. But in FOF2, which is the variable I was looking at, neither of these processes would be able to explain it really, based on these results.
Thank you. More questions? Let's thank Ingrid again.